today, as part of the basic electrical engineering, we have a session on the Kirchhoff laws. Let's begin. So the Kirchhoff laws, basically we have two types. One is voltage law and another one is current law. So we call it as the KVL, Kirchhoff voltage law. One more is KCL, which is Kirchhoff's current law. So before going into the in detail about this, first we'll see why we need to go for the Kirchhoff laws. So why the Kirchhoff has made these two laws? So this is because, so in the complicated circuits, so when if it is a simple circuit, like if you have a very less number of components, then easily we can analyze the circuit. But when we go for the some complex circuits where many components are there, then it is difficult to find the voltage and currents in the components. Okay, so here the Kirchhoff's laws gives us the flexibility to find the voltage and current in the circuit simple. Okay, so even though the circuit has many components, we can easily find the voltage across the any element and the current through the any element by using this Kirchhoff laws. And also we can easily find the equivalent resistance of the complex networks. So these Kirchhoff's laws are applicable for both AC and DC circuits. So we can solve any circuit by using the Kirchhoff laws. Now we'll see one by one what is KVL and what is KCL. So before moving into the detail about the KVL and KCL, to understand this KVL and KCL, we need to have some definitions. Here we call it as the circuit definitions, like what is branch, what is node, what is loop, network, circuit. These terms are frequently we use while solving the problems for the KVL and KCL. Okay, so here first we'll go with branch. So branch is nothing but it is an element which has the two terminals. Okay, a single element in a circuit is called as the branch. Here you can see in the circuit, like here we have one three resistors are there, and one we have the source. So how many branches are there here? So R1 is the one branch, R2 is one more branch, R3 is one more branch, and the supply voltage is one branch. So a single element in a circuit is called as the branch. Okay, now next coming to the node. So node is nothing but it is a point of connection of two or more elements. So now we know the elements. So this is the element, let us consider when the point of intersection of two or more elements is called as the node. So you can see here, this is the node 1 node where R1, R2 are connected to this point, and this is also a node. See, these two nodes are same. This is, we can consider it as a single node because there is no other element between these two. So we can consider it as a single node. So where R1, R2, R3 are connected to a common point. And even you can see here R2, R3 and this source are connected to one more common point here. There are no other elements are there in between these points. So we call it as a single node. Clear? And this is also one node because here the voltage source and R1 are connected to the common point. So this is we call node. So in this circuit we have three nodes. This is one node, this is another node, this is the another node where two or more elements are connected together. So that we call it as the node. Coming to loop. So here loop is nothing but a closed path. Here if you see in this circuit we have two loops. So this is one loop because if you consider these three elements, this forms a closed loop, right? You can observe this one clearly. This is closed loop. There is no like open path you can observe. And this is also one more loop. This makes the another loop with the two elements only. R2 and R3 makes a loop. So loop is nothing but a closed path. You can simply remember. Okay. The network. The network is nothing but it is an interconnection of elements or devices. So in these circuits we call it as the elements only. Okay, so network is nothing but the interconnection of elements, whether it is a closed or open circuited or closed circuited, the interconnection of the elements we call it as the network. So network may be an open circuit or it may be a closed circuit. Remember that point. Okay, so next coming to the circuit. So circuit is a same the interconnection of elements which forms a closed path. There should be a closed path, then only we call it as the circuit. Okay, see the difference between network and circuit. In network is also interconnection of the elements, but it can be open circuited or closed circuit. We call it as the network, whereas the circuit is nothing but it is also interconnection of the elements which forms the closed path. There should be a closed path, then only we call it as the circuit. Now I think you are clear about the circuit, network, branch, node and loop. So now we'll go for the KVL and KCL. So first we'll go with the Kirchhoff's current law. So KCL. So the KCL states that here at a node. So KCL is applied at a node. Remember, KCL we apply at a node. Already we know what is meant by node. So all the incoming currents to that node is equal to outgoing currents. Or you can say all the entering currents is equal to all the leaving currents. Another way you can define it as the algebraic sum of the currents at the junction. Junction is nothing but node here will be 0. Algebraic sum of the currents at the junction or at a node will be 0, or all the incoming currents are equal to outgoing currents. Here in this figure you can see this is a node. So here we have 5 currents are there. So I1, I5, I4, these 3 currents are entering into the node, whereas I2 and I3 are leaving the current, right? Leaving the node. So simply we can write it as I1 plus I5 plus I4 is equal to I2 plus I3. Or else we can write the same equation as algebraic sum. That is nothing but all the entering currents like I1 plus I4 plus I5 minus I2 minus I3 equal to 0. So both are same only. Okay. So here the same circuit which is representing the leaving currents. So like positively charged outgoing by the KVL, we should have a closed path. So the definition states that the algebraic sum of voltage drops in a closed path is equal to 0. So the algebraic sum of the voltage drops. See, this is the source, we have V1, and here one resistor we have, and another resistor here you can see this one. So the voltage drop across this resistor is V2 and the voltage drop across this resistor is V3. So here voltage drop is nothing but the current into resistor will give you the drop across the resistor. So already we have studied that the resistor will dissipate the energy, right, in the form of loss, or you can say temperature, heat. So here the algebraic sum of the voltage drops, that is nothing but V1 minus V2, V1 plus V2 plus V3 is equal to 0. Here one more resistor we have V4. So algebraic sum of all the voltage drops equal to 0. Or you can define the same statement as the algebraic sum of EMF applied, or the voltage. EMF is nothing but here voltage. You can don't confuse here. The EMF is nothing but voltage. So the applied voltage is equal to the algebraic sum of the drops in the elements. The supply is nothing but this complete voltage should be like appears across, drop across these 3 elements. So V1 is equal to V2 plus V3 plus V4. That is simple. The source or the applied voltage is equal to drop across the all elements. Okay. So here we need to remember that one point, that so while applying the KVL, the direction of the current plays a very important role. So first we need to determine the direction of the current. We need to allotted current direction. In this direction only we need to apply the KVL. So the same, this KVL is the we derived from the law of conservation of energy. The same, like we know already the law of conservation of energy, right? The energy neither can be created nor can be destroyed. It will be transformed from one form to another form. The same way here this voltage is fed to these resistors. The same like law of conservation of energy. Here this energy is dissipated in this resistors. So and it will be transformed in the form of either heat or some loss, you can say. So here we'll take an example, some like small example. How will you write this? See here. So this is a simple circuit which has the three resistors and one source. The source voltage is 45 volts. The resistor values are here given. And let us consider the current is I. Now simply apply the KVL. So we know that already the supply voltage is equal to drop across the each resistor, right? So drop is nothing but current flowing through the element into resistor across resistance of that resistor. So simply the 45 is equal to, so what is the current here? I into 5. So you can see here. So R1 into I plus R2 into I plus R3 into I. So these all are the drops. The sum of all these drops is equal to supply voltage, or you can tell it as source. So simply substitute the resistor values. So this is the simple KVL equation. You just simplify this equation so that you can easily get the current in the circuit. So one equation we have only one unknown. So simply you just add all these currents, add all these drops and find the current value. Now I think you are clear, right? Kirchhoff's voltage law, just we apply in a loop, closed path. The supply voltage is equal to drop across all, sum of the drop across all the elements. Now we'll take one small example to understand this KVL and KCL. So here we have taken one simple simple circuit. You can see here the circuit, so which has two loops and two sources and three resistors. Okay, so here if you want to apply the KVL, first we need to make the current directions. So I have taken the current direction as this, like this. Now just apply the KVL in the first loop. So drop is equal to the, supply is equal to the sum of these two drops, right? So in order to find the sum of these two drops, first we need to find current through the element. So here we know that the current I1 is flowing in this direction, but when it comes to this element here, for this element, for this element, the two currents are flowing. Like I1 is coming in this direction, means from top to bottom, where I2 is coming in this direction, means from bottom to top. So these two currents are flowing in this direction. Then the resultant current becomes I1 minus I2 when you are considering this loop, because this current is dominating when you are applying the loop, first loop. So we'll write the current flowing through this resistance is I1 minus I2. Now you can simply apply 10 is equal to the resistance of this element is 20 into what is the current flowing through this one, I1, plus what is the resistance of this one, 10 into what is the current flowing through this element, I1 minus I2. So this will give you simply the KVL of the loop 1. Now you apply the same loop, same like KVL in this loop. So in this loop 2 will give you this direction. So this is the direct current direction we have applied. So you just take the KVL also in the same direction. So the leaving current, like leaving polarity we will write. So if you apply the KVL in this fashion, so first we will get minus 5 plus minus, because current always enters at a positive terminal and leaves at the negative terminal, so minus. So now what will be the current in this element, because we are applying the in this loop, so I2 minus I1, because I2 is dominating, so I2 minus I1, so minus 10 into I2 minus I1, minus what is the current flowing in this element, 50 into I2. So this is the drop across this R2, so simply is equal to 0. I hope you are clear. See, simply you can write like this also. Supply, this we call it as the algebraic sum. This we call it as the, when supply voltage is equal to the drop across, sum of the drop across two elements. Just to like differentiate, I have taken these two types of equations. Okay, so even you can write it as minus 5 is equal to drop across these two. Like then we'll get 10 into I2 minus I1 plus 50 I2. If you send these two parts this right hand side, then you will get simply the same equation. Now we have the two equations and two unknowns. What are the unknowns? I1 and I2, and two equations. You just simplify this equation, find the I1. So simply we will get I1 is equal to 0.3235 amperes. Now we'll do the same circuit by using the KCL. So already you know that the KCL is applied at the node. So this is the node point, we can say, where the R1, R2 and R3 are connected. So you just simply apply the KCL here. Okay, so as this at this point we don't know the voltage, so let us consider the voltage V, because we don't know, right, the voltage value here. So let us consider V. Now apply the KCL here. So what is the current coming into the this node? So let us consider current coming is V minus 10 by 20, because the current is voltage by resistance, right? What is the voltage across this one? So we'll get V minus 10 voltage divided by 20. So what is the old current flowing through this R3? So we'll get simply V divided by voltage divided by resistance, V by 10, plus, so what is the current flowing in this element? So V minus 5 divided by 50, so is equal to 0. So see, let here we are considering that all the currents are flowing towards the node. We are assuming that, okay? So later you can change the direction if you get the negative value, okay? So for our analysis, we are considering, or we are assuming, all the currents are flowing into the node. So sum of the currents is equal to, there is no outgoing current, right? So we'll simply keep is equal to 0. So you have one equation. Now just simplify this equation. You have one equation and one unknown, so simply you will get voltage value where V is equal to 60 divided by 70 volts. Now we know the voltage, this is voltage value. Now we want current I1, right? So this is the current I1, right? So the current flowing in the first loop. So what is the current here? We are considering V minus 10 by 20, right? So simply you just apply the apply the voltage value here. What is 60 by 70? 60 by 17 minus 10 by 20. If you just simply solve this equation, you will get the I1. See, we got V value, right? What is the current here? V minus 10 by 20, right? This is the current. What is this current if you want? V V by 10. What is this current if you want? V minus 5 by 50. So these three are the three currents. So now we want this current. So means we know already the V value. So you just simply apply this value here and get the V1. So sorry, I'm sorry, I1. So I1 you will get 0.3235. Now in the both the cases you will get the I1 as same. So both the cases I1 as, whether it is by using KVL or KCL, will get the same value. So I hope you are clear with this KCL and KVL. Thank you for listening.
Hi friends, in today's session we are going to see about batteries and battery pack. Initially, we will see what is called battery. Battery is nothing but a device which converts energy stored in a chemical bond of a material into electrical energy by a process called as redox reaction. Redox reactions are chemical reactions in which electrons are produced or it can be accepted in a process. This is called as the redox reaction. Then coming to the categories of battery, see batteries are broadly classified into two major types. One is the primary batteries, another one is the secondary batteries. Primary batteries, they come under a one-way process. It is a one-way process where the process cannot be reversed. It is not reversible. You can just discharge the battery, but it cannot be recharged again. It is not reusable. For example, the alkaline consumer batteries used in flashlights, power TV remotes, clocks, etc. They they can be discharged, but it cannot be recharged again and used again. So those type of batteries come under primary batteries. Then we have secondary batteries. The process is reversible. The conversion process between electrical and chemical energy is reversible. Battery can be rechargeable. For example, we have a lead acid battery, we have nickel cadmium battery, and now we have lithium ion batteries also. So these batteries come under secondary batteries. Then comes uh, these batteries come under secondary batteries. Then comes So these batteries come under secondary batteries. Then comes, so these batteries come under, now we have lithium ion batteries also. So these batteries come under secondary batteries. Then comes how come under secondary. Secondary batteries. Then comes how battery pack is formed from a single cell that we are going to see. See, initially we will be having an electrochemical cell. Electrochemical cell is nothing but a device which is capable of generating electrical energy from chemical reaction or chemical energy from electrical energy or by both means. It is nothing but a basic device. See, a group of electrochemical cells together form a battery. Okay. Then comes the module. Group of batteries when they are connected either in series or parallel. these batteries can be connected either in series or parallel. It's a combination of series and parallel connection. We form a module. Then these modules again can be recombined in the form of series and parallel to form a pack. So battery pack is nothing but it is a combination of electrochemical cell which is in turn made into battery. Group of batteries are again converted into modules. Group of modules are again converted into a pack. Now we will see why group of modules are again converted into a pack. Now we will see why batteries are connected in series and in what case batteries can be connected in parallel. You see, this is the basic symbol of a battery. We will be having two terminals, one is plus, another one is minus, as shown in this diagram. When group of cells or a group of cells, when they are connected end to end is nothing but here when this negative is connected to the positive, again this negative is connected to the positive, then this negative is connected to some other positive. When the cells or batteries are connected end to end, such that there will be only one current flow. If you see, there is only one current flow, but the voltage drop across each cell may vary. Then we can say these batteries are connected in series. So I repeat, when batteries are connected end to end such that there is only one current flow in the circuit, but the voltage drop across each battery may vary. When batteries are connected in this form, we will say it is a series connection. Coming to the parallel connection, if you see here, when all the positive terminals are connected, see, when all the positive terminals are connected at one point and all negative terminals are connected at some other point, such that the voltage across all the batteries remain the same, but the current flowing through the batteries may vary depending upon the resistance or the capacity of the battery. So when the batteries are connected in this fashion, we call it as a parallel connection. But for practical application, we require both series as well as parallel connection. So in this diagram is the combination of series and parallel battery connections. See here, these two batteries, take 1 and 2. See, 1 and 2 are in series. Again, 3 and 4 are in series, but the combination are connected in parallel. So for practical application, we require both series and parallel combination battery connections. Now, for an example, if we are going to design a 12 volt 20 ampere hour pack, this is a battery pack with a rating of 12 volt and 20 ampere hour. Capacity of the individual battery we must know to create a pack. So each battery, let it be specification of 4 volt and 4000 milliamp hour. So how to design this 12 volt 20 ampere hour battery pack? See, initially we must find how many cells are connected in series and how many cells are connected in parallel. Cells I mean here, it is nothing but the battery. So you take this voltage, this is 12 volt. See here, we are having 12 volt. The voltage capacity, it is nothing but the nominal voltage. Here it is given as 4 volt. So you take the total voltage required divided by the individual nominal voltage. If you divide these two, we will get how many cells must be connected in series. So here we must have 3 cells must be connected in series to get this 12 volt. So voltage will get added up. When the batteries are connected in series. Then comes the current. See, totally we require 20 ampere hour. So total ampere hour divided by nominal single battery ampere hour. Here we are having 4000 milliamp hour, which is nothing but 4 ampere hour, which is nothing but 4 ampere hour. So if you divide 20 divided by 4, we will be having 5. So to increase the current, your battery pack must be connected in parallel. So you require 5 cells in parallel. To increase the voltage, your battery pack must be connected in series. So you require 3 cells in series and 5 cells in parallel. So the total number of batteries required is nothing but 3 into 5, which is nothing but 15 cells are required to form this 12 volt 20 ampere hour battery pack. Now you will see the modeling of battery pack and how the vehicle range is calculated. Considering the specification of a single cell, see here we will be having a manufacturer. Here we are considering the type of cell is prismatic cell, which is lithium ferrophosphate LiFePO4. The nominal voltage or the operating voltage is given as 3.2 volt. The ampere rating of the cell is given as 65 ampere hour. The weight of each cell is given as 1.8 kgs, and the dimensions are given. It is nothing but length, breadth and thickness. Okay, length, breadth and thickness. This is the volume. Dimensions are given. With the help of this, we are going to model the battery pack, and we are going to find the range of the vehicle. See here we are considering Mahindra E20P2 variant battery. So the capacity is nothing but, see here the battery pack capacity is 48 volts and we have 280 ampere. So we are going to just model and we are going to check whether our model is nearer or equivalent to the Mahindra E20P2 variant model. See here this is the modeling done in MATLAB Simulink. First of all, considering the voltage. See, we have 48 volt. We require 48 volt. This 48 volt is the total voltage. If I want the number of cells in series, I must just divide the total required voltage divided by individual operating voltage. So 48 divided by 3.2. See here, we are dividing. If I want the number of cells in series, I must just divide the total required voltage divided by individual operating voltage. So 48 divided by 3.2. See here, we are dividing. So that we will get the number of cells in series. So I am getting the number of cells in series is 15 cells. I must place 15 cells in series. Then comes number of cells in parallel. My requirement is 280 ampere hour. So the single cell has 65 ampere hour capacity. So to obtain 280 ampere hour, consider here, to require 280 ampere hour, I must divide the total capacity divided by the individual cell capacity. So 280 divided by 65. See here, they are dividing these two. So that I will get the number of cells in parallel. It is 4.3. It is 4.308. Okay. Then comes the total number of cells. We found 15 cells in series and 5 cells in parallel. So you must multiply these two. See here, they have taken this here output is 15. So they are multiplying this 15 with the number of cells in parallel, so that you will get the total battery pack total number of cells in the battery pack, that is 64.62. Now we have calculated the total number of cells in the battery pack. Then comes the battery pack rating. This is the battery pack rating. Battery pack rating we must already know. The battery pack rating is nothing but the current capacity, that is 280 ampere hour. This is the battery pack rating, 280 ampere hour. Then we must calculate the pack capacity. Pack capacity is nothing but the power delivered by the pack, total power delivered by the pack. See here, we are just multiplying the total voltage into total current. See here, we already know that power is equal to voltage into current. So we are multiplying 48 volt into 280 ampere hour, which will give me 13440. See here, this 48 volt and this 280 are multiplied, so that we are getting the total capacity of the battery pack. Now considering the weight of the battery, now we will see the weight of the battery, but as we already know, the battery pack voltage is 48 volt. This is given, that is our requirement. So just the 48 volt. Now we will see the battery pack weight. We know the dimension, this length, breadth and thickness of a single cell. So to get the volume of the battery pack, we must initially multiply everything. We must multiply the length, width and thickness. So here 228, 268 and 7. So here we are multiplying. Now we will get the volume of a single battery cell. Single cell we will get. This is the volume of the single cell. Now we must calculate for the total pack. See, the total pack is nothing but the total number of cells. So that must be multiplied by this total number of cells, which is nothing but 65 or 64. So this is multiplied, this volume of the single cell is multiplied with the total number of cells. See, this line is nothing but the total number of cells in the battery pack. This is for one cell and this is for total number of cells. So I will get the volume of the battery pack. Also I can easily find the weight of the battery pack. So see here, the weight of the single cell is given as 1.8 kg. So to find the total weight, just you are going to multiply the total number of cells in the battery pack into the weight of the individual cell. Just you are going to multiply. See here, this is the total weight of the cell in a battery pack. See, here the total number of cells in the battery, this multiplied by 1.8, which is nothing but the weight of the single cell, so that you will get the total battery pack weight as 116 kgs. 116 kgs is the weight of the battery pack. Okay, then comes, we have calculated the volume of the battery pack, we have calculated the voltage. Then next we will calculate the maximum battery pack voltage and minimum battery pack voltage. So you require cutoff voltage, the maximum charging voltage and the minimum discharge voltage you must have. So see here, for a single cell, the operating voltage is 3.2 volt. This is the operating voltage, but your cell can charge up to 3.7 volt according to the specification of the manufacturer. So it can charge up to 3.7 volt. Also it can discharge up to 2.5 volt. This is going to be the discharging cutoff voltage and this is going to be the charging cutoff voltage, and 3.2 is the operating voltage. So if I multiply this 3.7 with total number of cells in series. Because why series alone? Because only the voltage is increased when the batteries are connected, when the cells are connected in series. So we are considering only the cells in series. So this is 3.7 volts multiplied by total number of cells connected in series. So I am getting the value of 55.5, which is nothing but the maximum battery pack voltage. This voltage cannot go above 55.5. You cannot charge above 55.5 volt. Then comes what will be the minimum? What will be the minimum? So here the discharging cutoff voltage is 2.6. Sorry, it is 2.5. So again I am multiplying with the total number of cells in series, so that I am getting a value of 37.5. This is nothing but the minimum battery pack voltage. See here, the maximum is 55.5, minimum is 37.5. So in between you will be having the operating voltage, which will be the nominal operating voltage, is nothing but the 48 volt as per our requirement. So here it can go, you can charge up to 55.5 and it can go up to 37.5. This is the operating voltage. Then comes the what will be the usable capacity of the battery tank? As we already know, the total capacity of the battery tank is calculated as 13.4 kilowatt, but this 13.4 kilowatt cannot be used completely, because there is a concept called as depth of discharge, the maximum discharge that you can do in a battery. Here it is taken as 0.95. It is nothing but 95%. 0.95 is taken. So if I multiply the total capacity with the 95% of DOD of each cell, I will get the total usable capacity of the battery. Now finally we are going to calculate the range of the battery pack that we have set. Here depending upon the driving pattern, you will be having the consumption of power depending upon the driving pattern. See here, for a standardized driving pattern, the standardized consumption is taken as 88 watt hour per kilometer. For 1 kilometer, where we are consuming 88 watt hour. So this capacity, usable capacity, is divided by the actual consumption, power consumption, so that I will get the range of the vehicle. So the range is calculated by the total usable capacity divided by the standardized consumption of power per kilometer. So I will get the total driving range. This is how we calculate the driving range and other parameters of the battery. Thank you. We will see in the next session.